And so we're gonna finish up today with multivariate statistics and talk about some new tools for analyzing data. We'll use the box and whiskers plots. We've introduced those before, but today we'll look at them to see how to interpret them, especially if we have different groups of data. We'll look at a dendogram. So that's probably a new tool for you. Looking at Euclidean distance analysis. So we'll analyze that, and then we'll kind of introduce, I mean, we're talking about just really getting our toes into the shallow end of the water in terms of principal component analysis. We're not going to be able to do that any justice so that you'll be able to do principal component analysis, but we'll definitely, from today, understand when that might be useful. So when would you want to use PCA techniques? We'll learn that today. Being able to do them, I mean, you can go through the menu items and make Minitab do it, but there's more to it than that. You may apply it incorrectly, and so I would tread lightly saying that. Now, I wouldn't put that on my resume that I know how to do principal component analysis, but you could say that you've been introduced to Minitab and many of the graphical tools. So today we'll really focus on the dendogram and looking at box and whiskers plots and Pearson correlation coefficients. So with multivariate statistics, we're talking about more than one variable. You know, the calibration curve, we used an analysis of variance, but that was really just one variable, concentration, and we looked at how the signal depended upon that. But if you think about evidence, it has multiple properties. It's got color, it's got particle size. You know, you may have a couple of different packets of a suspect substance, and they might have exactly the same concentration of, say, cocaine. But the properties may be different in other respects. They might be slightly different colors. So just because they have the same concentration of cocaine, the thing you're interested in, does not mean that they're the same type of powder. They could have different particle sizes, which is huge. In fact, a lot of times that's the difference between sort of counterfeit drugs and normal drugs. The particle size has a lot to do with bioavailability. And so if you did just a chemical analysis, you might say, yeah, these have the same amount of the active ingredient. But if one is in large chunks that don't dissolve well in the stomach, you're not going to get the active ingredient. If others are micronized powders, they might be instant acting. And that's how we play with some of the time release drug formulations, is changing particle size, changing coatings. The chemical concentration of the active ingredient may still be the same, 200 milligrams in this formulation and 200 milligrams in that, but one might be released over 6 hours and the other might be instantly absorbed. Okay, so there's lots of properties to the various components that we might be analyzing, whether it be evidence, and it's not necessarily some white powder in a plastic bag. I mean, it could be tablets or pills. And so what we need to do is this bottom term, this totality of circumstances, that's really the forensic mindset captured in a couple of words. For this to be a suspect situation, it needs to take into account the totality of circumstances, not just the properties of the material. So if you see a white powder, is that suspicious or not? You need to know the circumstances, don't you? If you're on the aisle with the baking goods and there's flour sacks everywhere and there's white powder on the floor, probably not suspicious, right? But if you open up, an envelope at the Secretary of State's desk and pull out, and the powder falls out of the envelope, all of a sudden it's a white powder, same powder looking, from the external properties, but a totally different circumstance. And now this is a very suspicious white powder. So that's what we mean by totality of circumstances, not just the properties of the material, but what are the circumstances surrounding its discovery. So let's look at this data analysis of these 3 seizures of cocaine. So that means you've got 3 packets or groups of packets of cocaine, and either they were bundled, I don't know what the different seizures are, but they were labeled A, B, and C. So there were 3 groups. And so we're going to analyze these 3 groups of seizures of cocaine and see what we can learn about them. See if they're all 3 the same or if there's any substantial differences between any one of the 3. Okay. So there's ways to do this in Minitab that are very convenient. We could do all of the same thing in Excel, but it would be less convenient. So the questions that we're looking at, the investigators want us to know, are these three groups the same? Or are they related in some way? Might they have the same source? Okay. Were they processed the same way? So let's look to the data and see what we can find. We analyze them, and they come out with three main components. They have cocaine, procaine, and caffeine. So in all three of the groups of packets, they have the same three substances, but there's different concentrations of these. Now, one thing that's interesting, this is an important skill that you need to learn. This is new information. It's not in your notes, so I want to add in a little bit more detail. Realized in the notes this term blocking wasn't well defined. And so I want to really focus in on that word blocking the data, because this may be a new use of that word blocking for you. So the case ID, if we just pulled 10 samples out of each seizure, we would label the group A as A sample number 1, A sample number 2, A sample number 3. And so if we just label those A1, A2, A3, A4, A5, it's going to confuse the statistical software because it treats A1 differently than A2. And we may want to group all the A's together. And so you've got to actually pay attention to how you put the label information into an analysis package. It makes sense to separate the number from the letter. And so we took this data that was given to us in terms of case ID, A1 through A10, and then B1 through B10, C1 through C10, and we split apart the numbers. Because really the sample number is not very important. The letter is more important. And this allows us to block it by letter. So over here we have seizure A, B, and C, and then pack 1 through 10 for each one of those. And so it's going to be able to combine in a statistical analysis. It can give us sort of the average concentration for group A and the average concentration for group B and group C for all three of those compounds. If we set up our columns correctly, then we can have a very easy time in the analysis. So we say that these are blocked by seizure A, B, and C. So blocking is another way of saying grouping. So if you have blocked data, you could say you have grouped data. But statistical term a lot of times is they call it blocking the data. It sounds unusual. You think blocking means stopping something, but we're just saying we've got a block A and a block B and a block C. And so this is a 3D scatter plot. And all 30 data points are on here. And because we've had that column with the labels A, B, and C, we were able to set that up as a category label. And so we have category A, category B, and category C. You see these up here, and those are the colors. So all of your A data points are black, and the B and C are red and green. These little dialog boxes here are just showing you in Minitab how you set up this kind of plot. What do you notice from the data? So this is the interactive part of the lecture. What do you see as students looking at this for the first time?
That group A has a lot of cocaine and caffeine.
Right. Yeah. And so you can look at the axes. So that's, this over here. It's even though it's cut off. This is the cocaine axis, and so A is strong in cocaine. This is the cocaine. Sorry. This is the cocaine axis. This is the caffeine axis, and so cocaine is high in A. And also, so is the caffeine. And then this is procaine, and it's kind of low in the procaine. And what can you say? Someone else tell me, what can you say about B and C? They're very similar, aren't they? They're kind of mixed in together. And so we definitely, just from this one plot, would be able to say there's a difference between A compared to B and C. Could we say there's a difference between B versus C? Not really, because they're all mixed together. You see that cluster of data. And a dendogram, which we'll use later, will take those clusters and analyze the clusters. So it's an automatic way to analyze the clustering of the data. Okay, so good. Those are the same things I observed. It looks like A is different than B and C. And it looks like there's a correlation. So even though it's really scattered, what this means is a negative correlation. So when procaine goes down, cocaine goes up. And when cocaine goes down, procaine goes up. So this negative slope here, if you look at those plotted towards each other, looks like there's a negative correlation. We can get a better plot to show that, but we kind of see that here in this data. We're going to get the same conclusions from just about every set of charts that we use. So it's going to sound redundant, but I'm just showing you that there's a lot of different tools, and you can get the correct answer from a lot of different ways. Okay, so here's a box plot, box and whiskers plot. So what we do here is we take the data, the graph variables are up here, so that's what's going to be graphed on the y-axis, and then the categories are going to be the seizure variables here, and so that's A, B, and C. So those are the categories along the bottom. So group A, group B, and group C are shown along the bottom. And so what are your conclusions here? Someone who hasn't spoken yet. Of course, you're probably going to have the same conclusions you had before, but I want you to use this chart to justify it.
How about ABC or the same?
How?
From the boxes, they go the same pattern.
The same pattern, yeah. So this is pattern recognition. Look at the patterns in the boxes, and look for comparisons. If you draw lines down here mentally between A, B, and C, look at the pattern in B. Medium, high, low. Medium, high, low. And then look at the pattern in A. High, medium, low. You see that A stands out as being distinct or different than B and C. Okay, so this looks like A is different than B and C. Wow. Okay. And so this one is a really confusing looking chart, but this is what they call it, a matrix plot of correlation. So it's every variable plotted versus every other variable. And so across this vertical axis, you have cocaine, procaine, and caffeine. And across the horizontal axis, you have cocaine, procaine, and caffeine. So it makes sense that if you plotted cocaine versus cocaine, you'd have a straight line. Okay? And procaine versus procaine, straight line. And caffeine versus caffeine, straight line. But we've also color-coded them based on A, B, and C. And so you use just those, this diagonal here. Can you make any conclusions? Look at this one. Notice how the seizure A is drastically different than B and C together based on the cocaine concentration alone. And so that's one conclusion you could get from this correlation chart. Do you see any other conclusions that you could draw from this chart? This is a kind of an ugly chart, but that's realistic. The data is pretty scattered.
Except for the procaine and caffeine, the group A black dots are almost always isolated from the rest.
Yeah. And so here in this case, they're isolated, and it looks like you could draw a line like this. Whenever you have this line like that, if you could draw a line, now it's scattered, that's going to be a R squared pretty low, R squared. But procaine is high when cocaine is low. Let's see. And then over here, cocaine is high when procaine is low. So this would be a negative correlation. And we have a negative correlation on the other intersect. So cocaine plotted versus procaine. So it's just the same chart kind of flipped on the diagonal. And we have negative correlations in both of those. We will actually be able to test that later on by running a correlation test on these. So this will give you a graphical image of the correlation, and you say, looks like there might be a straight line there. What's the r squared on that straight line? We can get that number. Okay, so that's something that we can do. So it looks like A is different than B and C, and that there's a negative correlation. So let's run the numbers on this. If we go to the stat menu, basic statistics correlation, and tell it to display the p-values, the null hypothesis is there's no correlation. Okay? So you got to know what your null hypothesis is. So this is going to say there's no correlation, and then it's going to analyze procaine versus cocaine, and procaine versus caffeine, and caffeine versus procaine. So the probability, the p-value is the probability that there's no correlation. And so here are the results. This is the menu item that you get. And we get this triangular matrix. It's it's really like the bottom 3 boxes on that previous chart. Okay. So this is the correlation of procaine and cocaine. And it's a negative correlation, meaning when procaine goes up, cocaine goes down. Okay, just ready to understand the sign on that correlation before we get to the p-value. A negative correlation means when one goes up, the other goes down. And then here's the p-value that there's no correlation, 0.003. So what we saw in the chart that was really noisy was a real effect. There's a 0.3 chance that just noise in the data gave that correlation. Okay. Now the others, it calculates all the correlation coefficients. Here's caffeine and procaine correlated to each other, 0.04, a negative correlation. But here's the probability that that number came about by just noise in the data. So an 83.5% chance that this is really 0. Okay. So we would not say that procaine and caffeine are correlated. Because look at this. This is the intersection of procaine and caffeine. So we would not say that those are correlated. But here's one we didn't see in the chart. We did not see the correlation of cocaine and caffeine. It was just small enough that we didn't pick up on it. But it says there's a positive correlation of cocaine and caffeine, and the p-value is 0.005. So our confidence in that correlation would be 99.5% confident that there is a correlation between those two. So this is the probability that there's not a correlation. So 1 minus that is the probability that there is. Is there anything I can clarify on this one? This is a nice analysis to run because it gives you hard numbers. The graphical tools are great for display and for discussion, but when you're going to write a report and you're going to say what the correlation is, the Pearson's correlation coefficient is good to actually calculate. And so looking at the box plot, we can kind of see some of these correlations. Notice that when cocaine goes down, so it was here, let's say if they took the amount of A, let's say A used to be twice as big, right? And they took half of A and made B and C. And they got rid of some of the cocaine and made up the difference with procaine. And so that's what we see in this correlation. We can't really prove that that's what they did, but that's a potentially logical explanation for why B and C are different and distinct from A. And then we see that small amount of correlation with the caffeine when cocaine went down and caffeine went down a little bit. Mainly, I think, because they added so much procaine that it diluted it a little bit. So. But you don't get numbers off of this in terms of the correlations. You can just see the patterns. And so you run the Pearson correlation to get the numbers. Now, let's go back to our algebra days when we were calculating distances between 2 points on a plane or in space. And what do? You take the differences in the x values, the differences in the y values, the differences in the z values, and you square all those differences, and then add those up, and then take the square root. And that's the distance between those 2 points. That's the Euclidean distance. Euclid meaning that that all the planes are actually parallel planes and it's not a curved surface. Okay, so in plane geometry, this Euclidean distance is shown here. What if we took in that scatter plot the two closest points and just kind of drew a circle around them? Okay, so this is just like a 2D representation of that scatter plot. We took all of our data up here. Let me do it with the pen so you can see it on the screen. We took all of our data and we said, all right, 2 and 3 are closest. And so we're going to combine them and create a point right there in the middle. And then we're going to recompute all of these distance values between that point and all the others. And we see now that point is close to point number 1. And so we're going to combine all of those 3, and put a point in the middle. And now we're going to compare that point using the distance formula to these distances. And we see now 4 and 5 are the next closest points. So we draw a circle around 4 and 5 and put a point in the middle. And then we calculate the distance between these two clusters, and we get our last little point. Why would we care to do this? Let's discuss. Just fun? Yeah, we got one vote for fun. Not even fun.
Let's just do that.
Yeah, that's right. Just for the grins. Yeah.
We're trying to see if things are related.
Mm-hmm.
So if it's you're testing, like if you put all 5 of them together, is that close enough to actually be considered all together? And then versus if they're split apart, is that
Mm-hmm. Yeah, and if you think about this we're just looking at a 2D or panel here. But in that 3D cluster plot, this would get points on top of each other, diagonal from each other. So it's going to draw little circles around all the closest points. And if some of those letters are B's and C's, then all the B's and C's are going to be clustered together, and all the A's are going to be clustered together before any A is clustered with any B and C. So this is a way to kind of capture when the data points, even though there's 3 dimensions, 3 different drugs, are clustered together. The cool thing about it is it doesn't have to stop at 3. It could go to 4, 5, 6. You can't do a cluster, a 3D cluster or a 3D scatter plot with 4 variables or 5 variables, but you can do a dendogram with 5 variables. Okay. And so how would you get past the third variable z? You just give it another name and calculate its distance. So this would be the concentration of procaine compared to the concentration of procaine squared, the difference squared, and then the difference in caffeine squared, the difference in cocaine or procaine squared. If you had a 4th drug, the difference in that squared. Take the square root, add them together, take the square root, and then you have the distance. In 4 dimensions, you have the distance. In 5 dimensions, you have the distance. So this is a really quick way to produce a really easy diagram to understand. So if you have all your data points labeled, what 2 data points are the closest? Notice the y-axis is distance. So always look at the axes. This is distance. So these are the farthest apart. And these are close. So you can look at this right away and see what the 2 closest data points are. Right here, B6 and C8. They have almost exactly the same properties in terms of cocaine, procaine, and caffeine. And they're in 2 different seizure packs. And so that's the closest one. Where's the next closest one? You just move up until you see the next horizontal line. Yeah, so that from my view, that looks like that one's a little closer. It's B8 and C6, and then B2 and B7, and then it's combined with C2. So you just move up and you see all of these things clustered. Here's a B9 and C4. And this keeps going, and then eventually we get to an A group. A9 and A5 have similar concentrations. But what do you see in this dendogram? What conclusions can you draw?
It is very different from B and C, the way that we go all the way to the left, and they hardly interact with anything else, or they don't interact with
Right. So this whole group here, these are all mixed together, aren't they? And so this is one major group, and this is another major group. So we really have two groups. All the A's are close to A's, and the B's and C's are all mixed together. You could see that in the scatter plot easily, if you could make a scatter plot. But let's say we had 4 dimensions, or 5 dimensions, 4 or 5 compounds we were comparing. We could still generate this plot, but we couldn't generate the scatter plot. We could still generate the correlation matrix. It would just have 5 or 6, be a 5 by 5 square if we had 5 variables. But this one is, again, a cluster analysis, a dendogram. If you can interpret these, it's a nice skill to have. So let's go back now and look at the control charting. The Minitab does control charting, but I think it's just as easy to use Excel for your purposes in tracking your data because you're so familiar with it. But Minitab does have some automatic control charting. But let me pause. Let's go back and make sure, because we're leaving this cocaine example. And was there anything in any of the plots, Boxplot, Scatterplot, the Dendogram, that you want clarified before I move on? Because we're about to shift gears. Yes?
Can you explain the clustering data again? Like, I still don't understand why you found the point in between on top.
Okay, so if you'll notice here, B6 and C8 have this little low bar here. Okay? That, if you come across here, is the actual distance between those 2 points using this formula right here at the top.
Okay.
So that top formula, only instead of X, Y, and Z, it's the cocaine concentration, procaine concentration, and the caffeine concentration for each of those data points. So you take the difference in cocaine and square it, and the difference in procaine and square it, and the difference in caffeine and square it, and add those squared values together. You square them because you want them all to be positive. You don't want things to cancel out. So you have, and you don't want the order, which one you subtract from which to make a difference. So you square those values, and then add them together and get the square root. And that gives you the distance. And so if you've done that for all of the data points, the smallest distance you combine first, just to show that those 2 data points are very close together. So that's what was meant by these 5 little panels.
Okay.
So we have our data up in the top left, and we're going to do this analysis. We combine points 2 and 3, because those were the closest 2 points. And say these points are so close, let's just treat them as the same point and redo the clustering. And then we notice that they're very close to point number 1, so we combine them. So it's sort of just drawing circles around our data. On that dendogram, 2 and 3 would be joined, and then 1 would be added in. And then over here, 4 and 5 would be joined, and then all of them joined at the end.
Okay.
At the end of the dendogram, everything's always joined together. But you're just kind of seeing what happens on the way to that path. So let's see if we can't draw a dendogram using this information. So I think there's one behind here, but I'm just going to draw a new one. So we have 5 data points. So we have 1, 2, 3, 4, and 5. And so that's our x-axis. So if you want to draw your own, that's fine. And so after this first panel, we calculate the distance between all our data points, and we find the smallest distance is between 2 and 3. And so we're going to join 2 and 3. And then we redo the analysis with this new data point, the center of that little ellipse. And we see that it's close to number 1. And so then we would have this little mark right here go up to the distance to 1 and come down. Okay, because we joined in, that was going from here to there. Oh, sorry, here to there. Okay, mark an X, do that. And so then we redo the analysis and we see 4 and 5 are combined. So when we go to here, we have a mark, and it's a further distance than those other 2. And then last, we have everything combined together at the distance. between those two. Does that help?
Yes.
Excellent, yes. And so if you were to look at this dendogram, how many groups of data would you say? So I'm going to say how many groups? That's a good question I could ask. So when I'm looking at this, I say, well, it really looks like 2 groups because 1, 2, and 3 were combined fairly early, and 4 and 5 were combined late, and there was no connection between the left side and the right side until the very end. That's a bit of a judgment call, but we're looking at that and say, okay, I have 2 groups of data. I have 1, 2, 3 as a group, and 4 and 5 as a group. If you look at the plot, you can kind of see that. You see that 1, 2, 3 are clustered together, and 4 and 5 are clustered together. The interesting thing is it's obvious when we can look at a plot, but if you have 4 variables or 5 variables, you can't make the plot. And so a dendogram is really helpful if you have 4 substances or 5 substances that you're analyzing in these samples. Yes.
Is there any like statistical tests to like definitively say that there's so many groups rather than like use like the judge?
Yeah, I don't know of any. There may be, but I don't know of any. Yeah, it's a good question. Okay. Yes.
So for, especially when you group like 1, 2, and 3, is there like a midpoint formula for when you do this?
Yeah, that's good. It would be a little bit more algebra, but yeah, you would just take half that distance, and then you have to figure out on that line. You go halfway on that line. Let's see. I bet, yeah, you could hit it by taking the average x value, the average y value, the average z value. That would be the midpoint.
Okay.
So you could just, x1 minus x2, you just take the average of those 2 points, and that will, let's say they're like this. You take the average, that gets you halfway up. And then over here, you take the average of that one, that gets you halfway over. And if you plot that point halfway up and halfway over, you get the midpoint. And so, yeah, we could do that. And so that would be the point that you would then compare in the next step with all the others. Now, that's really tedious if you think about doing that by hand. Okay, but that's what computers are for. You just say, generate a dendogram, and it'll produce this distance matrix in clusters, and then you get the plot. So these are some fantastic statistical tools that save you a lot of time. So let's look at some of the control charting tools in Minitab, because again, if in the future, if you don't necessarily want to use Excel, if you want to use Minitab to track things, then that's great. This is a repeat of an earlier slide. It's just talking about how this will bring it up. That one or two people are confused in their reports about what I mean by data-driven process. And this slide is explaining that. So again, you want the data to drive your action. When it's out of control, then you intervene. But if it's not out of control, you don't intervene. And we have a high bar for intervening. Right? If you're constantly taking action, you're actually becoming part of the uncertainty. You're actually introducing mistakes and increasing the noise in the data by always fiddling with the machine. So you have a high bar for intervening, and that would be that 2 sigma. So roughly, 95% confidence that the system is in control, and you want to make sure it's really out of control before you take action. So if it's above or below 2 sigma, it's about 2.5% chance of being above or below. And so only in those cases where it's 2.5 times out of 100 are you going to intervene, because it may drop down below. It may correct itself because it may just have been a random error. So you can do control charts. You just put your data in Minitab and then update the control chart, and it has a control charting tool. The cool thing about it is here, you may have to go to the notes to actually see the details, but these are tests to test if your system is in control or not. So let me just read some out to you because you might not be able to see the fine print. Okay, so you can set this variable k for all these different tests. And so when it refers to k, it's referring to these settings over here. And so here, 1 point is greater than k standard deviations from the center line. And this is set at 1, but for our control chart, we set it at 2. And so it's going to flag a data point if it's more than 2 standard deviations from the center line. Here, you can have k points in a row on the same side of the center line. If you're worried about drift and your instrument starts and you get 9 data points in a row on one side, then you can set that as a flag. See, we only have one action limit flag in our control chart exercise, but we could be ridiculous and require all 9 of these. Okay, and you would be writing reports every day because something's going to happen. Now, think about the data: 9 points in a row on one side of the distribution. I mean, it doesn't say how far away on one side, but think about what the probability of that is. If we've got a Gaussian curve and there's the center line and I'm on one side, what are the odds of being on one side or the other? Yeah, 50-50, exactly. And so if I'm on one side, it's a 50-50 chance. The next day, I've been there twice now. It's 50% or 0.5 times 0.5. So now it's 0.25, 25% chance of being on one side. So it's 0.5 to the second power. Okay, what about third day to the third power? Fourth day to the fourth power. What about the ninth day? It's 0.5 to the ninth power. That's not controlled. Right? It has drifted. It's so rare that you would have 9 data points on one side of your average that there's something wrong. That's not random variation. And so you might want to take action. You might want to see if this is drifted. Okay? It hasn't drifted out to 2 sigma past on one side, but it's definitely moving. And so this is one of the tests. You can have k points in a row, all increasing or all decreasing. So now this is not just on one side or the other with further and nearer, but this is one side and then a little further, and a little further, and a little further. So 6 times drifting. Then you could flag that. And you could tune these different variables to your system. This was a weird one. K points in a row, alternating up and down. Now that's, maybe your process is susceptible to that, but this would be up and down 14 times. So is that random? This is just trying to find things that are not random. This one is k out of k plus 1 points greater than 2 standard deviations on the same side. So, you just got a bunch of different tests that you could run. So here's a pipette calibration. So putting 10 drops on there in the training set, just measuring the mass delivered for a pipette. And we did that 10 times and then started control charting. And this is the control chart that Minitab produces. And so notice that this is just 0.63 times the standard deviation. And that's that t value. And it didn't flag this one, but it flagged this one, even though it looks like it's still inside. And it put a number 7 on there. And it flagged this one with a number 7. And then this one is a 1, and that one is a 1. And so you get this control chart, and you get color-coded data points that turn red when they're out of control, and it gives you a number as terms of the warning. Now, this is nice to know about Minitab. There's charts that it produces, but with every chart, there's also a thing called a session log. So it's kind of like the text output of what the program's doing. And so you need to go look at the session log to see what these warnings are. And so here is the session log related to the control chart. And it says test 1, more than one point more than 1 standard deviation from the center line. And it test failed at points 17 and 18. And then that number 7 was test number 7. 15 points within 1 standard deviation of the center line. And it failed at points 15 and 16. So this is a weird test. Within 15 points, within 1 standard deviation of the center line. I said it's an invalid warning, but I don't know. It may not be. When would this be strange? So you guys do your control chart data and you set up your warning limits and your action limits. And your warning limits are plus or minus 1 standard deviation. So that's what this is looking at. And it says it has 15 points in a row inside that watch limit, inside of 1 standard deviation. That's why. What is it trying to tell you with this warning? And this is something you have to really puzzle over. So you tell me where those lines come from, the standard deviation lines. During the trial period, yes. So you have 15 days of training data, and that gives you your standard deviations. And then you start control charting, and you see 15 days where it stays within the watch limit. Not the action limit, just the watch limit. It's within 1 standard deviation for 15 days. What's it trying to tell you if that's a warning? Okay, there's a sticker on the line. They're like, all right, I just got real. What is the training period an attempt to do?
Isn't that supposed to like stabilize things, like standardize things?
Well, we're not actually doing anything to the system. We're just observing it. So we're not stabilizing the system, and I think that's an important thing to point out. We're not stabilizing the system, but we're learning about it.
Is it telling you that you may have a new standard deviation because it's like your data might be like tighter, so then you're
Yeah. So we've learned about the data, and then maybe something's changed. Maybe the data went from being noisy to tight. And if we're trying to control it to the best that we can, we've got noisy limits, and now the data's tight. And so we might be able to shrink our limits in. It's just warning us that our standard deviation may not be correct anymore. So we won't use that test, but we could. You know, let's say during your trial period you had a couple of outliers that totally widened your standard deviations, and now we don't have those. Our standard deviations are off. So we're not just learning about the magnitude of the data and how it changes, but also the tightness, the precision of the data. How tight can it be controlled? So good job for getting in. And good job for speaking up. Okay, give me one. Making a shot at it. All right. So let's look at principal component analysis. So this is changing gears. We've got cocaine, procaine, and caffeine, but what do we do when there's a fourth variable added? It's really difficult. We could do a dendogram still, but we can't do a scatterplot. But let's say we still wanted to look at the data. We need to do dimension reduction or data reduction. So we need to find a way to plot the data, but we can't plot 4 variables. And so mathematically, this reduces what they call the data space. We have 4 axes, and we're going to reduce it to 3. Or actually, what happens is they reduce it to 2. We try to take all the different axes and reduce it down to 2. So we can plot it on a flat plot. And so the takes linear combinations of the data fields, and those are called factors. And then we look at the percent variation covered by those factors. So if we have cocaine, procaine, and caffeine, can we reduce it if we come up with an equation that is some coefficient for caffeine, some coefficient for procaine, and some coefficient for cocaine? So we might find 2 equations that are dependent upon those variables that help separate the data. So let's explain this with the session log. Think about all of the 3 columns of data. We have the concentrations for all 3 of our drugs. and we could do a linear regression on those. And so we could say y is equal to some combination of x, y, and z. And let's see, y, no, that doesn't make sense. T is some combination of x, y, and z. And so that's going to have coefficients in front of those. And these are the coefficients that came out of the PCA results. So it's saying that factor 1 here has this equation. So the value for factor 1 is 0.92 times the cocaine concentration, plus, or I should say minus 0.68 times the procaine concentration, and 0.657 times the caffeine concentration. So now I have factor 1, which is a single variable that is dependent upon 3 of the other variables. But I'll have, for every data point, I'll have a single number, factor 1 number. And then I can have a different combination. I can do a linear regression in a different direction and get factor 2. This is the equation for factor 2. It's equal to negative 0.002 cocaine, so it's really not including the cocaine at all, plus 0.67 times procaine, plus 0.706 times caffeine. So this is the equation for factor 2. And down here, this is the percent variance. This is capturing 58% of the variability in these factors, and this is capturing 0.32% of the variability. And that adds up to 0.9. So we're capturing 90% of the scatter in the data by using these two factor equations. Now that looks really confusing, and it's just numbers, but what happens then is when you plot it, you get this separation of the data. So we plot factor 2 by factor 1, and we get spread in the data. Now, this may not look impressive to you because we were able to plot the correlation plot earlier and it looked very similar to this. But this is a really useful tool if you've done the correlation plots, you've tried 3D scatter plots of all 3 combinations of the variables and you haven't seen any pattern at all. You do PCA analysis and sometimes it will draw out a pattern that you were not able to see. And so this might be the first time that you saw a separation between A versus BC. Okay. And so that's when it's super useful. You look at all these other tools, box plots and everything, and you just don't see a pattern, and you run PCA analysis. Sometimes these factor equations can pull the data apart, and then you can make a confident claim about the different factors. Yes?
Can you explain what unrotated and rotated mean?
Yes. And so notice how the top one, this percent variability that's captured, is 0.5 and 0.3. You can rotate those equations and how they're combined and sort of trace through the data in a different manner in order to make those percent variables equal or close to equal. And so notice the difference here between unrotated, they're not quite equal, and rotated, they are closer. 0.458 and 0.443. So that's what the rotation does for you, is it tries to get factor 1 and factor 2 to capture the same amount of scatter in the data. So you can, but visually you might be able to see more of a distinction in the unrotated or in the rotated, so it's good to try both. And I couldn't see the difference, so I only just showed one of the plots. But it gives you both. If it doesn't, I have to go back and look at Minitab. If it doesn't give you both, you can it's a checkbox. You can rotate it or unrotated. And so you can go in and look at it either way. That's, again, just getting your toes wet in PCA analysis. It's a way to pull the data apart, and it's super useful if you have more than four or more variables that you're trying to analyze. Let's go see if there's a Kahoot on this one. I think there is. trying to get me to pay for it. Free is good for me. Maybe later. I'm trying my patience. What's that?
It's got the little Valentine's and stuff.
Oh, I did?
Yeah. Compared the O's together. And it's got a little heart.
Oh, yeah, that's sweet.
Oh.
Everybody. Oh. All right, here's your code. 446688. Let's see, 5, 10, 15, 23 people. Yay, okay. Are you ready? It's only 3 questions, but it probably sparks some discussion. How many clusters are present in this dendogram? Dun, dun, dun. Ooh, it's hard to see. Good. You want to look at it again?
Yeah.
Discuss it? Okay. Oh, so it's color coded, right? But could you make a case for 4?
Yeah.
What would be the evidence for 4? This little group here, yeah, yeah. So again, it's a bit of judgment. Nobody likes that, but you know, you can make a case for 4. 3, 2 is right out, and so is 6. But I would say that, that's clearly 3, maybe 4. Okay. Cocaine in A is significantly different than cocaine in B and C. How do you know this? You don't know which one you clicked?
Like when I went to answer it, it had already gone to this one.
Your thumb had just hit it, yeah.
Oh,
Yeah, so yeah, B. And so let's look at the picture. It says, because the cocaine boxes do not overlap. So what does it mean by the boxes? These gray boxes, right? But so what? What do the gray boxes represent? Well, it's close, but what is it actually? When they draw that box, what is the lower part of the box and the upper part of the box? Mm-hmm.
The range?
No? The range is whisker to whisker. No? 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 This is great. It's one of those weird words. Okay, that's pretty vague. Dendogram's pretty weird. No, it's not skewness or kurtosis. Those are weird too. Yeah. So maybe that wasn't specific enough. Remember the quartiles. So what did that? I just gave you a hint. Quartiles. But what would the box represent then? Which quartiles? Yeah. So there's the first, second, third, and fourth because it's quartiles. There's 4 of them. Okay. And so it's the barrier between first and second and third and fourth. Yeah, so it's the second to the third, it's encompassing the second and third quartiles, the middle group. Okay. The barrier between the second and third quartile is the mean. And so then capturing the mean and the two quartiles. So 50% of the data is inside the box, right? The quartiles that divide the data into 4 groups, 50% is in the middle box. So this is saying 50% of my cocaine data. Oh, I don't get a pen on there. Oh, there it goes. Okay. 50% of my cocaine data is in this box. And over here, 50% of my cocaine data is in that box. And also the ranges. The whiskers are the ranges. And so the highest cocaine values on this one and this one are below the lowest cocaine value on that one. If the boxes overlap or the ranges overlap, you really don't have confidence in saying that they're different. So look at the caffeine. This box overlaps with that box, which overlaps with that box. So you could not say, just looking at this plot, that the caffeine was different in any of these 3. Okay, but you can say, wow, the cocaine's very different. I've got one box that doesn't even touch the range of the other boxes. These 2, look how cocaine is almost identical in terms of their boxes. And then the procaine is different than these, but maybe not statistically so. This range kind of hits that box and overlaps with the range of the mean. Yes?
So whenever you think about it, you have to think about it as you're putting the boxes on top of each other and see if they
Yeah, so just slide them over on that y-axis. Just slide them down to the, like if you turn the chart on its side and they all fell down to the bottom, would they hit each other? Yeah. Okay. And so these cocaine boxes wouldn't hit each other. These both would fall down and hit on top of each other, but this one would be by itself. And so you're just looking along that y-axis to see if they overlap. Yeah. Okay. Last question. What is the probability that there is a correlation between procaine and caffeine? Procaine and caffeine. So this is playing around with the null hypothesis and double negatives. I hear a lot of groans. It's like you punch it and go, oh.
I kept looking at the cocaine and caffeine, and I was like, no, that's the right answer. And then I was like,
yeah.
That's why it took me so long to punch it in the
Yeah. I went and gave a lot of time on this one so people could sit there and I smell smoke, wheels are turning. That's right. 2 more people. Make your choice. Oh my gosh. Well, at least y'all knew it was one of the bottom 2, right? So 16.5%. Because think about this. This is the p-value that the null hypothesis, that the probability of the null hypothesis is true. And the null hypothesis is no correlation. Okay? So 1 minus this is the probability that there is a correlation. So 16.5% chance that there is a correlation between these 2. Not good odds. Okay. All right. Yeah. Oh, sorry. Yeah, cut that quick. Didn't give people the victory lap. All right. So next time, bring your questions. We'll go over the practice exam and answer questions, look at vocabulary, talk about the Excel spreadsheet. So good class today. Thank you for interacting.